In this video I will be isolating chromium metal from stainless steel. I would also recover a nickel, but to my surprise it wasn't there. I was looking for some straightforward guide, at least on YouTube, and I didn't find anything, so here it is, I guess. Anyway, so first of all, this is absolutely not cost effective. If it wasn't me, I would rather buy some chromium powder and then process it into its salts, or preferably buy particular salt, of course. So here you can see that I'm already cooking some stainless steel tube in sulfuric acid with a little bit of hydrochloric acid to speed things up. I'm doing this in huge beaker, and inside this beaker I have smaller beaker filled with water to condense the vapors. Kinda poor man's reflexing setup, basically. Now a little bit of backstory. So I was about to machine this tube for my glassblowing lathe, and I thought to myself, what if I used acid and sponge and rub the outside walls of this tube? Well, it's basically an iron, so it should be quite quick. Yeah, and guess how that turned out? Exactly. Nonetheless, the next day I was expecting this tube to be quite corroded, basically because of hydrochloric acid. For example, this kit of kitchenware, it's stainless steel, at least it says so. And what you can do is put the salty water there and in few weeks it's mess. So in my eyes the corrosion resistance of stainless steel to chlorine ions seemed to be very low. So at this point I was quite curious what the chromium and nickel content of this steel is. I was expecting something around, I don't know, 60%. In reality it's about 20% of chromium there, and that's all. Yeah, and maybe about 2% of copper for some reason. Okay, so our tube is cooked and I'm going to transfer it to the beaker. I mean the leftover solution, not the tube. Just in case, I am filtering this through some coffee filter, and there was no insoluble residue. Okay, next step is to precipitate the hydroxides of the metals. From what I have read, the chromium-free hydroxide forms an hexaqua complex in strongly alkaline solutions. That means that it's soluble in a hydroxide, basically. And that's not happening there, so either it's chromium 2 hydroxide, which properties I don't really know, or I don't know. After the precipitate settled down, I siphoned the remaining liquid into other container. Then I added some hydrogen peroxide to this liquid, assuming that it contains only some sodium salt, so nothing happens. And that's true, nothing has happened, so good. Anyway, the point is that I'm trying to dilute the hydrogen peroxide, because in the next step I expect quite vigorous reaction. Okay, so I slowly poured back the hydrogen peroxide solution, and it wasn't that bad actually. And what we are doing here is that we are oxidizing iron 2 hydroxide to iron 3 hydroxide, or iron 3 oxyhydroxide, or what it is, and the chromium 2 hydroxide to chromium at oxidation state 6, so it forms sodium chromate. Iron will remain insoluble, so it's easy to separate it from chromium by simple filtration. So once again, I let things settle and siphon sodium chromate. In case you missed the first warning, don't touch this thing, this is cancer. Then I transfer the sodium chromate into the hugest beaker, and in the next step of reaction we will acidify the solution to form sodium dichromate. So solution will change the color from yellowish to orange. Now we want to reduce the oxidation state of the chromium to +3, so it's much safer to handle. Well, we have quite a few options there. This could be done with primary alcohol such as ethanol, sulfite ions such as potassium or sodium sulfite, or bisulfite as I am aware. I've tried both of these, but it's quite messy, at least with ethanol, and quite smelly with bisulfite. Then you can bubble hydrogen through the solution, and finally we can oxidize this even more to the oxidation state +7. Chromium in this oxidation state is not stable in water solutions, and conveniently it will reduce itself to the oxidation state +3. This is the way to go, because otherwise you will have to boil away the hydrogen peroxide that's remaining there. I don't really understand how it can persist there, because it is supposed to oxidize the chromium, but I guess magic? Anyway, so let's proceed. Immediately after addition of hydrogen peroxide, the solution will change color from orange to, well, some darkish violet blue, and then transition slowly to green. This camera is not 100% correct in the color representation, but it's fairly close. Now in the smaller scale this reaction is quite fast. I was a little bit afraid, to be fair. Okay, so what we are left with is chromium-free sulfate, chloride, or whatever acid you added in. And now that the solution is quite a little bit safer to handle, we can remove hydrogen peroxide. And this is usually done by boiling the solution, so off to the hot plate. After about half an hour of boiling, we can let this cool and proceed to the next step. And that is precipitation and cleaning of the chromium salt. It seems that the chromium carbonate is only thing that is really practical and insoluble, so we will go with that. You can precipitate it with sodium hydroxide or ammonia, but you will eventually lose some chromium there. So I am adding sodium bicarbonate to the solution. When the reaction is done, large flakes of sodium carbonate will start to form. You can simply filter this off and clean it, and that's quite pure salt of chromium what you have there. Here I'm filtering chromium carbonate through some coffee filters. Nice greyish moldy color. And originally I wanted to extract metallic chromium, so I'm going to redissolve this in acid. I tried using electrolysis and displacement reaction. What you see here is displacement reaction, and I'm trying to displace chromium with aluminium. To my surprise, aluminium does not seem to be reacting with chromium sulfate there. The only thing that's happened is that the solution has changed the color because it has been reduced. On the other hand, the electrolysis just oxidized the solution to this orange-red color. I tried this with chromium sulfate and chloride, and the result is the same. I was using positive carbon electrode and tried to deposit chromium on some copper plate. I have not tried what Wikipedia suggests, and that is to suspend positive electrode in sulfuric acid with some membrane to prevent mixing the solution with sulfuric acid, and that way to prevent oxidation of the chromium sulfate. That's quite a lot of work, and I'm happy to give up right there because I don't really need chromium for anything. I'm just playing around with stuff. Okay, so thanks for watching and have a nice day.